All right, welcome everyone to today's seminar. Today I'm happy to introduce Dr. Julia Stawarz. Dr. Stawarz is a Royal Society University Research Fellow in the Department of Physics at Imperial College London. In 2021, Julia was awarded the Winton Award in Geophysics from the Royal Astronomical Society, and in 2018, she received the Basu Early Career Award from the American Geophysical Union. Her research focuses on in situ spacecraft observations to examine the fundamental physics of turbulence, magnetic reconnection, and other multi-scale collisionless plasma processes across a variety of plasma environments that are accessible in near-Earth space, including Earth's magnetosphere and the solar wind. I'm happy today to have Julia here to talk with us about reconnection observations from the MMS mission. And with that, Julia, if you would like to take it away.
Okay, thank you for that introduction. So hi, everyone. I'm Julia Stawarz from Imperial College London. So I'm going to be talking today a bit about the work that we've been doing with the magnetospheric multi-scale mission, looking at kind of small-scale turbulence-driven magnetic reconnection that's embedded within the Earth's magnetosheath. Right. So stepping a bit back from just the magnetosphere for a moment. So turbulence is the term that we use to describe the complex, highly nonlinear behavior of fluid and plasma systems. It's relevant for systems throughout the universe, both within neutral fluids like we would find here on Earth. So things like the Earth's oceans and the atmosphere, as well as the atmospheres of other planets. So you've got these great pictures of, the atmosphere of Jupiter or of the cloud tops of Earth, or even these kind of cool images from NASA looking at the kind of turbulence within the ocean. Here on Earth, it's also relevant for laboratory plasmas. So, it comes up in kind of confinement for fusion-related stuff, and also people do kind of fundamental physics and studying the dynamics of turbulence within the laboratory as well. And then, of course, in space plasma systems, turbulence is thought to be an important process across a variety of different length scales within the universe. So in systems ranging from the solar corona and solar wind, planetary magnetospheres, both that of the Earth, which I'll be talking about today, as well as the magnetospheres of other planets within the solar system. It's also relevant for kind of the interstellar medium, as well as, things like accretion disks. So like those that you might find around black holes, and even at the really large scales in the universe, there are kind of astrophysical observations of turbulence in kind of the intra-cluster medium, so at the scale of galaxy clusters, right? And so within all of these systems, turbulence generates fluctuations across a wide range of different length scales. These fluctuations play a role in generating the kind of structure that we see within these systems. The dissipation of the fluctuations plays a role in kind of heating and accelerating particles within the plasmas, and it can also play a role in kind of mixing together different plasma populations. Right, and so even though we kind of know the equations that in principle describe kind of hydrodynamics or plasma physics, one of the big challenges in turbulence is that because it's such a highly nonlinear system, we don't necessarily know the exact kind of nonlinear solution to all of these highly interacting structures within a turbulent environment. And so some of the questions that we're trying to answer with spacecraft observations provide us a means for looking in detail at these kind of turbulent systems that we have access to in near Earth space, in particular the solar wind and planetary magnetospheres, to try to understand these processes a bit better. If we look at the spectrum of the fluctuations that are generated by turbulence. We know that turbulence tends to generate a broadband spectrum of fluctuations in space, right? And this is created because the nonlinear interactions within these systems cause fluctuations to exchange energy between different length scales. And typically this transfer of fluctuation energy will be from kind of large scales to small scales in what we call a cascade. So energy, you drive energy into the system at large scales, and then it will non-linearly interact and kind of incrementally transfer energy to smaller and smaller length scales, kind of populating this broadband spectrum. And phenomenologically, you can come up with kind of a description of how the turbulence behaves, and usually expect to get kind of power law behavior to the energy spectrum. Lots of people look at the details of what this spectral slope is. And the reason that they do that is that you can link back the spectral slope to kind of assumptions about what the underlying physics associated with these nonlinear interactions is. However, the spectrum itself doesn't give you all the information about the turbulence. So there's lots more things that in principle one can look at. And if we're looking at space plasmas, which are often collisionless, then as you get to smaller and smaller scales, as we all know as space physicists, eventually your kind of fluid MHD approximation starts to break down as you approach the characteristic length scales of the ions. And this causes the behavior of the turbulence to change. And it can change in a variety, because of a variety of different things. It can change because the kind of nonlinear interactions within the system change, right? So you change how kind of rapidly you're exchanging energy from length scale to length scale, and that will change the slope of the spectrum. And you can also start introducing pathways for dissipation as you get down to the scales where the fluid approximation breaks down. And that can essentially take away energy from the fluctuations and reduce the, steepen the power spectrum. And of course, in a collisionless plasma, there are a variety of different mechanisms for actually dissipating the energy within the system. You might have things like wave particle interactions or resonances between the turbulent fluctuations in the waves. You can have sort of nonlinear structures that are formed that can potentially lead to acceleration of particles and dissipation. So things like kind of the electric field structures like double layers or phase space holes that may accelerate particles or trap particles. And you can also have things like magnetic reconnection that may play a role in energy dissipation. I'll be talking a little bit more about that today. And so broadly speaking, there are a variety of different questions that we kind of care about in studying collisionless plasma turbulence. So some of those are, how do the nonlinear dynamics actually behave across these different length scales, both in terms of how they relate to and balance the kind of linear dynamics, which would give you waves, as well as how they change as you go across the different characteristic length scales. And all that can change the sort of structures that are formed by the turbulence and how you distribute energy and how quickly you dissipate the energy. We also care about how energy dissipation is actually occurring. So one of the big open questions, one of the things that I'm particularly interested in, is looking at what processes actually end up being responsible for dissipating energy within the plasma. And there can be a variety of different mechanisms, and it's not guaranteed that the mechanisms responsible for dissipation are going to be the same across different plasma systems. So that may be influenced by the ambient plasma conditions or how you're driving the turbulence or the boundary conditions. And so we need to look at a variety of different turbulence systems to understand it. And then there's also a question of how turbulence impacts the environment that you find it within. So this may be things like in the solar wind, we care about how quickly your what the heating rate, dissipation rate of the turbulence is, because in principle that may be related to the heating rate of the solar wind. But in magnetospheric systems, where often you have these turbulent plasmas within kind of a confined region and interacting with the boundaries, there can be other ways that it's impacting the system. So this, you may perturb the magnetopause, for example, through turbulence, or you can kind of radiate waves out of a confined region of turbulence that may propagate towards the aurora, for example, if you're looking at the magneto tail. right? And all of these are interesting questions, right? So if we go back from Fourier space and look at what's going on in physical space, one of the things that turbulence does is that by generating these kind of complex interacting structures, you tend to twist up and compress and tangle up the magnetic field lines within the plasma. And in principle, this can create a multitude of different current sheets, and these can be potentially be sites for magnetic reconnection to occur. And it's been thought for a long time that magnetic reconnection plays a fundamental role in turbulence. However, traditionally, it's been quite a challenging thing to really look at, both observationally and in simulations. And there's a few different reasons why we care about the kind of role of reconnection within the turbulence, because it both kind of plays a role in the nonlinear interaction or nonlinear coupling between the magnetic field and the particles. That is to say, when you get a magnetic reconnection event, you convert some of the magnetic fluctuation energy that's embedded within a current sheet that you form and transform that into the kinetic flow energy of the particles. And of course, the jets that you form will then feed back into the turbulent environment. And so it's one of the ways that you exchange energy between the magnetic fields and the particles within the turbulence. So it's one of these kind of nonlinear dynamics that we kind of care about when we're trying to understand how turbulent systems behave. And the other thing that reconnection can do is that it can potentially facilitate the dissipation of energy through the acceleration and heating of particles within the wider reconnection event. And of course, there's kind of a energy partition problem within magnetic reconnection of understanding how much energy is going into kind of heating particles versus how much is going into the acceleration of jets, right? And so understanding that can help us to better understand kind of the role that reconnection might play in dissipating the turbulent fluctuations in collisionless plasma. And so one of the things to recognize about kind of reconnection within a turbulent system, in contrast to, say, the very large scale reconnection events that you would get on the magnetopause, for example, or in the magnetotail, which are really dictated by the kind of large system scales in the magnetosphere, is that the current sheets that you form within the turbulence are going to have kind of a finite length scale that's going to be set by kind of what the characteristic length scale of these twisted magnetic field structures that are formed by the turbulence are. And within turbulence, you would expect that the kind of size of these twisted up magnetic fields is going to be related to what we call the correlation length, which is essentially sort of, if you look at kind of the average scale over which the magnetic field is correlated with itself, it'll pull out kind of the size of these, say, magnetic islands if you're thinking in 2D, right? And so the current sheets, which they form at the interfaces of these structures, are going to be constrained in some way by that correlation length of the turbulence. Of course, any individual current sheet can have different length scales or have a different length along the outflow direction, say, but you know, there'll be some distribution that's dictated by the size of these turbulent fluctuations, right? And so one of the things that we've begun to recognize, motivated by some of the observations that I'll be talking about a bit later, is that if you have these finite length current sheets within a collisionless plasma, if the length of, if your correlation length is relatively short compared to the characteristic length scales of the ions, this can have a significant impact on kind of the nature and behavior of magnetic reconnection. And this is led to what's come to be known as electron-only reconnection. That is, if your kind of length scale of the reconnecting current sheet along the outflow direction is comparable to the ion scales, then the magnetic field will relax before the ions have had a chance to really fully couple into the newly reconnected field lines, and therefore you won't significantly accelerate kind of ion outflows like you would normally expect. And the result of this is that you end up getting very fast electron outflows, virtual suppression of the ion outflows. And it turns out that the thickness of the reconnecting current sheet can be much thinner, and also the kind of reconnection rate can be much faster than you would otherwise expect from the standard sort of picture of reconnection where ions couple into the dynamics and are accelerated out by ion flows. And there's been some really nice simulation work by Prayash Piakurel looking at this in kind of idealized numerical simulations where kind of took a kind of standard Harris-sheet sort of reconnection configuration and then artificially set the length of the current sheet along the outflow direction by just setting the size, his box size. And you can look at what the kind of ion outflows that you get are compared to what you would expect them to be from the E cross B drift. And you can see that if your kind of current sheet length is around larger than kind of 40 ion inertial lengths, then you get the reconnection outflows that you would expect to have. But as you get shorter and shorter, the speed of your ion outflows decreases, and eventually it's virtually non-existent. And so you can see kind of in the physical domain what that looks like. So you've got this electron-only reconnection event where there's really no response going on from the ions. You have these electron outflows that are clearly there. And so you can see what that looks like in 1D cuts down at the bottom. And then in the kind of standard ion coupled, where you have a much longer current sheet, you can see these clear ion outflows being formed and corresponding electron outflows. And so in the context of turbulence, the reason why this might matter is that if the reconnection is playing a significant role in turbulent dissipation, for example, or a significant role in the kind of nonlinear dynamics, then this is going to impact how you're partitioning that energy between the ions and electrons. So you may have differences in how much you heat ions versus electrons, depending on if you have this electron-only reconnection going on or not. Right, and so I thought I'd just also plug that as well as kind of the numerical simulations and observations that I'll be showing later from MMS. There's also been some recent work in the laboratory looking at this electron-only reconnection. So there's been some experiments at West Virginia University looking at setting up reconnection events with little flux ropes, and the size of these is such that you get this kind of electron-only reconnection where it seems that only the electrons are being accelerated by the reconnecting dynamics. And so the magnetospheric multi-scale mission provides us with a kind of unique opportunity to look in extraordinary detail at both turbulence in general, as well as these kind of turbulence-driven reconnection events, which have traditionally been quite challenging to look at. So MMS is a 4-spacecraft mission. It's orbiting Earth. And the unique thing there's several unique things about MMS. So one of them is that it has the formation size of the MMS spacecraft is incredibly small, going down to as small as 5 kilometers separation, which in the Magnetosheath is approaching the electron length scales, so it's a few times the kind of electron length scales in the Magnetosheath. It makes kind of 3D electromagnetic field observations, and crucially, it makes really high resolution particle measurements. So you get full 3D velocity distributions for the ions at 150 milliseconds and the electrons at 30 milliseconds, which allows us to really identify reconnection outflows at very thin current sheets, which we need to look at this electron-only reconnection. And because we have the kind of multi-spacecraft measurements, it's 4 different spacecraft, typically in a tetrahedral formation, we can actually compute kind of gradients. So you can compute things like the current or a variety of other gradients. And people have made great use of that to really try to look in detail at the nonlinear dynamics as well as kind of dissipation processes in the turbulence. Right, so I'm sure everybody in this audience probably is aware of this, but just so we're all on the same page, right? So the Earth's magnetosheath is the region of shocked solar wind plasma that's downstream of the bow shock. right? Here's just an example of what that looks like for an MMS data. So over on the right-hand side of the plot, we've got the solar wind where you have this fast anti-sunward flow. You have the sharp discontinuity, which is the bow shock. And then you have all of these kind of fluctuations downstream and lower speeds, and that's the magnetosheath. All of these fluctuations that you're getting downstream of the bow shock correspond to lots of small scale current sheets, which you can see down in this bottom panel. And those are, in principle, sites where magnetic reconnection could be occurring. Right, and so within the Earth's magnetosheath, there are a variety of different ways that these fluctuations might be generated. It could be, some of them may be associated with the fact that you have kind of turbulence in the solar wind that are just propagating through the shock. You could have kind of processes that are occurring at the shock that are exciting new fluctuations and say stirring up the turbulence even more. You can have instabilities within the magnetosheath itself. Say you generate temperature anisotropy and generate, say, mirror modes or things like that that generate new fluctuations within the magnetosheath proper. And you also have these kind of turbulent, these newly stirred up fluctuations interacting with each other as they move around the magnetosheath. And so as a result, you end up with varying turbulence properties across the magnetosheath, depending on both kind of how far away you are from the shock, whether you're downstream of a quasi-parallel or quasi-perpendicular shock, potentially depending on, you know, the ambient properties in the particular parcel of magnetosheath plasma that you're in. And so there have been various works looking at how these turbulent fluctuations vary across the Earth's magnetosheath. There was this nice one by Huang et al. In 2017, which was using cluster observations to look at the spectrum of the fluctuations in the magnetosheath and how that varies across the magnetosheath. And what you often find is if you look kind of near the subsolar point, you tend to have rather shallow spectral slopes at MHD scales and what are kind of typical kind of power laws at kinetic scales. And if you look further down in the flanks, you tend to get something that looks more like the classic sort of Kolmogorov picture of turbulence, where you have a minus 5/3 spectrum, and again, a similar sort of sub-ion scale power law slope that's quite typical of turbulence. And if you look at what the spectral slopes at the MHD range are across the full magnetosheath, you kind of see this trend of when you're kind of closer to the bow shock and you're at the day side, you have sort of shallow power laws. And as you go further into the flanks, you start to pick up these steeper Kolmogorov-like power laws. And there's been various speculation about why this might be. There may be a relationship to whether you're downstream of the quasi-parallel or quasi-perpendicular shock. It could be related to you know, how much time the turbulence has had to evolve. Maybe you stir up the fluctuations right near the bow shock, and that generates kind of a new kind of unprocessed set of fluctuations that need time to non-linearly evolve and develop into the kind of the fully developed turbulence spectrum. And I don't know that the answer to why you have this variation across the magnetosheath has been fully explained yet, but there are various ideas for why. So the point is that we can look at different kind of regimes of turbulence and stages of evolution of the turbulence as we look across the magnetosheath. And so I'll be making use of this when looking at reconnection. In terms of looking at reconnection within the magnetosheath, there's been kind of a large body of work that's been picking up some more momentum lately in various different directions. Right? So we have these classic observations from cluster, which provided evidence of potential evidence of magnetic reconnection that's going on within the turbulent fluctuations within the magnetosheath. But with cluster, because the particle measurements weren't high enough resolution, the kind of evidence for magnetic reconnection tended to come from the electromagnetic field. So in this example from this Reconnection et al. Nature paper, right, you have this reversal in the BL component of the magnetic field. So that's that reconnecting magnetic field component. And they've were able to directly observe this EM electric field, which would be the reconnection electric field. And that was kind of the key evidence they had that reconnection might be going on at this current sheet. And you can also compute things like J.E and see that there's an associated exchange of energy from the magnetic field going into the particles. And if you compute the E cross B velocity and use that as a proxy for kind of a higher resolution estimate of what your kind of outflows are going to be doing, you can see this L component of the E cross B velocity, which is presumably associated with the outflow. But with the resolution particle measurements with cluster, it was difficult to really directly see those reconnection outflows. And so with MMS, which makes much higher resolution particle measurements, one of the things that we've been able to do is directly measure the reconnection outflows. And in this paper by Fan et al., he actually found direct evidence of oppositely directed electron outflows observed by two of the different spacecraft. So this top set of panels is from MMS-3, and this bottom set of panels is from MMS-1. Again, you can see this blue component of the magnetic field is the reconnecting component, which undergoes a reversal, as you would expect for reconnection. And then if you look at the third panel down in each of these, this has the electron velocity. And in blue, you can see a positive electron jet within this current sheet and a negative electron jet within the current sheet observed at the two different spacecraft. So this was kind of the smoking gun evidence that you have kind of active reconnection going on because you have these oppositely directed electron jets in the within this current sheet. And this was this Fan et al. Paper was one of the kind of first papers that proposed that this electron only reconnection may be going on, because he found a number of examples of reconnecting current sheets within the magnetosheath, and none of them seemed to show clear evidence of ion jets. But as well as this Fan et al. Paper, there's been a number of different studies looking at the kind of current sheets and possible reconnection events within the magnetosheath. And another area that's begun to be looked at in detail since MMS has been launched is kind of reconnection as it's associated with the bow shock, right? And so there's been a number of numerical as well as observational studies looking at bow shock simulations, and you tend to generate lots of fluctuations right in the vicinity of the bow shock, and then those evolve into what would become the magnetosheath. And so there's been a lot of work looking in what people call the transition region of the bow shock at reconnection events that are occurring here. And looking at how those reconnection events, the properties of those reconnection events depend upon the bow shock properties and how they might evolve into the magnetosheath fluctuations going downstream. So the work I'm going to be talking about is looking at further downstream from the bow shock, kind of within the magnetosheath proper, and looking at what we can learn about reconnection that's driven by turbulence by looking at the magnetosheath. So instead of linking it to, say, the bow shock properties directly, I'm looking at how it relates to the overall kind of turbulent conditions within the magnetosheath. Right. So in a recent survey that was published earlier this year in Physics of Plasmas, we went through and tried to do a big kind of statistical survey of turbulence-driven reconnection events in the Earth's magnetosheath using the kind of high-resolution measurements that we now have from MMS. And the kind of questions that we were aiming to answer with this is how common magnetic reconnection is in the magnetosheath, as well as if we see evidence for this kind of transition from ion-coupled to electron-only reconnection as we look in different intervals of magnetosheath turbulence, right? And so to do this, we identified 60 intervals of kind of the highest resolution MMS burst data across the dayside magnetosheath. This scatter plot is just showing the location of all of those. And so you can see that we have kind of coverage across the dayside, both at the subsolar point and going out in towards the, down towards the flanks of the magnetosheath. And here's just an example of what one of those intervals looks like. And so the kind of features we aimed for in selecting these intervals is that we wanted kind of fairly long continuous intervals of burst data, so we could get good estimates of the turbulence kind of statistics within the intervals. And we also wanted it to be kind of relatively homogeneous. So while there's kind of fluctuations throughout the interval, we didn't want large scale gradients across the interval. And then we also had some various other criteria that I'll talk about in a little bit. Right. So with MMS, even though we have these, sorry. Is it not coming? Oh, there it goes. Okay. So with MMS, even though we have kind of these multi-point measurements from the different spacecraft, in order to get the multi-scale kind of turbulence statistics that you usually want to look at, so things like the spectra or the correlation functions, which go into computing this correlation length, or structure functions, it really requires you to have a variety of different spatial separations to be able to directly measure those kind of multiple length scales that are generated by the turbulent fluctuations. Typically, MMS is going to be in a tetrahedral formation, so we get a look at different directions within the plasma, but roughly one length scale. And so we need a way to try to probe the different length scales within the plasma. And so one way you can do that is by appealing to Taylor's hypothesis, which is the kind of approximation that you would usually use with single spacecraft measurements to get information about turbulence. And it's effectively just assuming that all of the turbulent structures are just being advected in the background flow over your spacecraft and not significantly dynamically evolving over the time it takes for them to propagate over the spacecraft. Right, so that you can relate the temporal structures you see in the time series directly to spatial length scales, right? So that your length scale that you're looking at is just going to be related to the velocity, the background velocity times the time scale. And this is a very good assumption in something like the solar wind, where you have very supersonic and superalfanic flow, but the kind of validity of this becomes a bit more tenuous in something like the magnetosheath, where you've gone through the bow shock and the speed of the flow has slowed down, right? But with them, since we have multi-spacecraft measurements, we can make an attempt at checking the validity of the Taylor hypothesis for the different intervals we look at. And so we actually did that for all of the 60 intervals. And in fact, one of the selection criteria we had was that the Taylor hypothesis seemed to be working fairly well for the interval, right? And so the way we did that was to compute what we call what's called second order structure function. So it's this kind of difference in the magnetic field squared and averaged over the kind of entire interval. So you're looking at the statistic of the turbulent fluctuations. It's directly related to the correlation function as well as the power spectrum. And so we can compute that both assuming the Taylor hypothesis from the individual spacecraft, as well as by using the direct differences between the spacecraft that we have. And because the spacecraft is in a tetrahedron, we get differences in different directions relative to the flow and magnetic field, right? So then we define this ratio of the structure functions computed in these two different ways, and then we can look at how that varies as a function of the orientation that you're looking with respect to the field. And you would expect that if you're looking along the same direction or in as the background flow, then you should have good agreement between these estimates if the Taylor hypothesis is working, right? And here's just a few examples from these different intervals, and you can see along the flow direction given by these dashed lines, there's kind of good agreement. This ratio is roughly equal to 1 for all of these intervals, which is what you would expect if the Taylor hypothesis is valid. And another thing that kind of gives us some indication that this may be working correctly is that we tend to have this kind of systematic trend in how this ratio varies as a function of angle. And it turns out this is consistent with what you would expect for kind of anisotropic turbulence with respect to a background magnetic field. And there's a dependence on kind of how anisotropic the turbulence seems to be on how strong the background magnetic field is, with it being more anisotropic if there's a stronger background field. So that seems to be all kind of consistent with what we would expect. And it seems that the Taylor hypothesis is working fairly well, at least at the scales that we can directly measure. Okay, and so then once we did that, we went through all of our turbulence intervals and computed the correlation length of the magnetic field, which we expect to be related to how constraining how long the current sheets within the turbulence can be, right? And so the way you do that, so you have your time series of magnetic field fluctuations. You can compute the autocorrelation functions with the correlation between the fluctuations in the magnetic field across different spatial separations, or correspondingly different temporal separations in the time series. You get the correlation function. You expect in a turbulent environment that will decrease towards 0 as you go towards larger length scales. And the scale of that decrease is going to be your correlation length. Right, so then we can estimate what the correlation length associated with this correlation function is, and get kind of a value for what the correlation length is for each of the intervals. And we checked that, the value of your correlation length appeared to converge fairly well. So you can look at kind of progressively increasing the fraction of the time series that you use to compute the correlation length and look at if it converges to a fixed value. And so for all the intervals that we had, it seemed to converge to a constant value. So we have a well-characterized correlation length for each of these intervals. And if we look at what that looks like across the magnetosheath, we see there's a systematic trend where you tend to have shorter correlation lengths near the subsolar point and longer correlation lengths as you go into the flanks. And it tends to vary from around 10 ion inertial lengths or so up to several tens or even hundreds of ion inertial lengths in the flanks. And so the thing that's interesting about this is right in this range where we would expect to see this transition from having kind of electron-only reconnection going on in the turbulence to having more kind of ion-coupled reconnection going on. And so we then went through and systematically looked for magnetic reconnection events and tried to characterize the properties of those reconnection events. So to find the reconnection events, we had kind of a partially automated procedure for doing this. So first we looked at we set a threshold in the magnitude of the current and looked at all of the most intense current structures within each of the intervals. In this case, we selected 3 times the RMS current. We went through and identified each of the individual current structures that were above that threshold. And for each of those current structures, we went and rotated it into a local current sheet coordinate system using kind of a hybrid minimum variance analysis technique, where the N component is the cross product normal and will be the normal to the current sheet. The M component would be the guide field direction. And then the L component would be the flow direction if it's a reconnection event. And then once we've rotated each of these into a local current sheet coordinate system, we had kind of an automated check for some conditions that you would expect for a reconnection. So looking for reversals in the BL component of the field, as well as perturbations to the electron flow that were greater than kind of 70% of the L component of the alphane speed. And the reason we looked specifically at the electron flow is because you would expect that both electron-only reconnection and ion-coupled reconnection will have signatures in the electron flow, but electron-only reconnection wouldn't necessarily have a signature in the ion flow. And then once we had these kind of automatically selected candidate events, we then went through and manually looked at each of the events to see if they had kind of other features that seemed consistent with the kind of quasi 2D guide field reconnection sort of picture. Right, so for example, here's just an example of one of these current sheets within this interval. So you can see there's a strong current. You have a reversal in the BL component of the magnetic field. And then within that, you have this electron flow perturbation that seems to be qualitatively consistent with being a magnetic reconnection event. And I'll show you some of the other kind of features that we looked at on the next slide. So once we did this manual down selection of events, we ended up with 256 magnetic reconnection events across the 60 intervals, and that corresponded to about 10% of the kind of most intense current sheets within the magnetosheath having evidence of magnetic reconnection, which I think is a relatively large fraction. So it seems to be a common feature, at least in magnetosheath turbulence. So here are just a few example events of the different kind of reconnection events that we found in this survey. So typically when we're looking at this magnetosheath turbulence, we expect that these kind of reconnection structures are being advected over the spacecraft in the background flow. So typically what happens is MMS is going to cross through this event along kind of, 4 closely spaced trajectories. Usually it's roughly normal to the current sheet, but it'll depend a bit on how the current sheet is oriented with respect to the flow. And if we're lucky, then you'll get 2 spacecraft on either side of the X line, and you can see oppositely directed jets, but often you don't have that situation, so you'll just be cutting across one side of the event. And so we see a variety of different kind of types of events, both ones that seem to only have electron signatures with them, and ones that have ion outflow signatures as well. So these are 2 different examples of those kinds. So on this side, we have kind of an ion coupled reconnection event. So you have this peak in the current, this reversal in the BL component of the field. If we look at each of the individual magnetic field signatures, there's actually kind of this partial bifurcation of the current sheet, which may be consistent with like starting to go into the transition from the kind of ion diffusion region into the more fully coupled ion region. You have this electron jet signature within the current sheet, as well as this ion flow signature that's centered on this magnetic field reversal. This ion signature is actually well below the expected alphane speed based on the reconnecting component of the field. And so this may only be a partially coupled ion jet, at least at the location where we crossed through the event. And then if we look at the electromagnetic energy conversion signatures, so J.E, you can see this positive peak. So energy is going from the field into the particles, which you might expect at a reconnection event. If we look at the BM component of the magnetic field, we also see that there's this kind of, there's an overall guide field, but there's a little bipolar perturbation to the field on either side of the current sheet. And that seems to be consistent with what you would expect for the Hall fields based on how you've crossed through this event. For this other event, we didn't see a clear signature of an ion jet, but we did see a signature of an electron jet. And similarly, we have this BL reversal in the magnetic field, as well as a bipolar signature in the BM component that would be consistent with the Hall electric fields that you would expect. And again, we have this positive J.E signature. And so for any given one of these events, it's really hard to know for sure if you're crossing through, say, an electron-only reconnection event where the ions are never coupling into the event, or if you're just crossing through the electron or the inside of the ion diffusion region for an event, so that you just aren't seeing the ion jet, which may exist further away. And so in order to try to sort out if we're seeing electron-only reconnection or not, then we can look at the kind of broader statistics of all the events that we're getting. And where we're in principle crossing at a variety of different distances from the current sheet, and see if we're having over prevalence of events where we're just seeing the electron jets as opposed to the ion jets. Additionally, so these were both events that where we crossed kind of nearly almost normally to the current sheet. And so we just saw one of the outflows. We also have a few events where you kind of skimmed along the current sheet, and we actually, I think for some of them, we actually crossed kind of over the close to the X line, right? And so this is kind of an unusual configuration to get, just because the cross section of a finite size current sheet is going to be smaller if you're just skimming along the current sheet. And so it's more likely to cross normally. But for this particular event, I think we kind of skimmed along and went over the X line. And so you can see that here. So we have this BL reversal of the magnetic field again. You see this bipolar signature in the electron flow again. There isn't a clear ion signature, so it goes from a positive jet to a negative jet. You could see a signature in the electric fields that would be associated with the kind of Hall electric fields as you cross through this current sheet. And we actually saw, one of the reasons that this was a particularly interesting event is that we saw this really clear reconnection electric field signature that was above the uncertainty and the electric field measurements. And of course, because there's a high guide field, it corresponds to a strong parallel electric field. And for this particular event, we actually did some comparisons with particle and cell shock simulations of kind of self-consistently generated reconnection events within a shock layer, where you tend to get lots of these electron-only reconnection events. And the kind of strength of this reconnection electric field is much larger than you would expect for ion-coupled reconnection, and roughly consistent with the sort of reconnection electric fields that you see in the shock simulations. And so there's some evidence that you have this kind of electron-only reconnection going on, because you have these very high reconnection electric fields, at least for this event where we had this really clear observation of the reconnection electric field. So for each of these 256 different reconnection events that we had, I went through and characterized various properties of the reconnection event. So how thick the current sheet was, as well as how fast the ion and electron outflows were. And in the case of the ion outflows, that was only if we saw a clear evidence of an ion outflow. Right? And this is just showing how those different parameters relate to each other. So on the x-axis, we have the current sheet thickness, and on the y-axis, we have the peak jet speed that was observed for the ions and electrons. And we find that a lot of the current sheets tend to have thicknesses that are below the ion scale. So you have these kind of electron scale reconnecting current sheets, as you might expect for electron-only reconnection. There's sort of a weak anti-correlation between the current sheet thickness and the electron jet speed. So the very thin current sheets tend to have these fast superalfanic electron outflows that are approaching the electron alfane speed, which is consistent with what you would expect for electron-only reconnection. And as you go to the larger ion scale current sheets, you tend to have slower electron outflow speeds. And then the events that we did see ion jets on tended to occur at the ion scale current sheets, which again may be consistent with kind of having a population of electron-only reconnection going on and a population of kind of more ion-coupled reconnection going on, where the current sheet is kind of roughly constrained to the ion scales, and you, in principle, have both ion and electron outflows. We can then look at how these different properties, so the current sheet thickness and the jet speeds, relate to the correlation length, and see if we have kind of a variation in the distribution of reconnection event properties depending on what the correlation length is. So this is showing the correlation length for the intervals versus the current sheet thickness. And so for any given interval, which has lots of different reconnection events, there's going to be a distribution of different current sheet thicknesses. And so what we would expect to see is that because you're kind of constraining the length of the current sheet in an average sense, you may shift that distribution towards being kind of sub-ion scale electron-only reconnection at short correlation lengths if you have this kind of process of electron-only reconnection going on in these intervals. And we do seem to have some evidence of that going on. So at large correlation lengths, the distribution of points is roughly centered on the ion inertial length. So you have kind of ion scale reconnecting current sheets. And then as you go down to kind of 20 ion inertial lengths or so for the correlation length, the thickness of the current sheets The distribution tends to shift to smaller scales where you have kind of a population of sub-ion scale reconnecting current sheets going on, and that would be consistent with electron-only reconnection. And so we can look at this in a slightly different way, so kind of cut this scatter plot in half around 20 ion inertial lengths and look at what the cumulative distribution functions are. And you can see that there's this kind of shift in the cumulative distribution function to have more kind of small sub-ion scale current sheets when there's short correlation lengths compared to large correlation lengths. And this seems to be a statistically significant shift in the distribution. So it seems to indicate that we do have this kind of transition from having more electron-only reconnection being more prevalent in the turbulence at short correlation lengths, and then you get more kind of ion-coupled reconnection as you go to larger correlation lengths. We can also do the same thing for the jet speeds. And again, we see seems to have a bit of a potentially a transition from having kind of slower electron outflow speeds for large correlation lengths and a bit of kind of an uptick in the distribution as you get below kind of 20 ion inertial lengths. And if you do the cumulative distribution function thing again, there's a bit of a difference that may be consistent with what you would expect for electron-only reconnection. That is, you have a higher prevalence of faster electron jet speeds at the expense of slower electron jet speeds for short correlation lengths, but it's a bit harder to tell in this case if this is a statistically significant difference in these distributions, unlike the kind of thickness of the correlation length result. But there does seem to be something that's consistent between the two. And so the takeaway point is that, in a turbulent environment, depending on the scale at which you kind of drive the turbulent fluctuations, which is setting this kind of correlation length, you could change the nature of the reconnection events that are being generated between kind of ion-coupled reconnection, where the ions are participating in the dynamics, to this electron-only reconnection, where you only have electrons. And that may impact the partition of energy between ions and electrons. So we can then go through and look at kind of what role the reconnection, because we have this large survey of reconnection events, we can look at what role they may be playing in turbulent dissipation. And so we can make kind of a estimate of what the kind of dissipation rate associated with the ensemble of reconnection events may be in the these different magnetosheath intervals. And this is just kind of a rough sort of back of the envelope sort of calculation where you can estimate what the fraction of particles that are accelerated by any given, kind of processed by any given reconnection event is, kind of what fraction of the available magnetic energy that was reconnected is converted into heating as opposed to particle flows, how much reconnected energy, how much energy you're actually reconnecting, so what's the available magnetic energy to reconnect, and then how fast is that reconnection occurring, right? So what's the reconnection rate effectively? You can convert that into a dissipation rate, which if the reconnection were the only process responsible for turbulent dissipation, then that would should be equivalent to your cascade rate of the turbulence. And so a number of these different things we can actually directly estimate from our survey of reconnection events. So things like, what the available magnetic energy is, what this kind of dimensional bit of the reconnection rate should be, as well as get kind of an estimate for kind of the fraction of the domain occupied by reconnection events and kind of how much of the particles are being processed by the reconnection based on kind of our occurrence rate of reconnection, as well as kind of assumptions, bounds on kind of how many particles would have been exposed to that reconnection event, either by how many particles were in the reconnection event to begin reconnecting current sheet to begin with, as well as kind of how many are in the broader kind of magnetic islands that are inflowing into that reconnection event. We'll put kind of bounds on this kind of number of particles that are being accelerated. And then there are some unknowns, right? So we need to figure, ideally we would want to know what the reconnection rate for each of these individual events is. typically that would be around 0.1 for ion coupled reconnection, but there's evidence from simulations that it can be much faster for electron only reconnection. And then there's this question of how you're actually partitioning the energy between accelerating jets and heating particles. That's a bit unknown. There's some constraints for kind of ion coupled reconnection that Tai Fan has done, but what that actually is for electron only reconnection is a bit unknown. But if we put in kind of reasonable estimates for what these might be based on simulations, and then this is just assuming that you get kind of the same overall conversion of energy into heating and electron only reconnection as you do in ion coupled reconnection, which may, but potentially partitioned differently. Then you get a cascade rate that's around 10 to the 4 to 3 times 10 to the 6 joules per kilogram second, which doesn't mean that much. But if you compare it to estimates of the turbulent cascade rates that people have made for the magnetosheath using other techniques, so third order structure functions, or kind of phenomenological estimates of what the cascade rate is based on the fluctuation amplitudes, this is broadly consistent with the kinds of values that you find in the magnetosheath. So that would indicate that the reconnection events that we're observing may be playing at least a partial role in dissipating the energy within turbulent, within the turbulence in the Earth's magnetosheath. Okay. Another thing that we can look at is what impact these reconnection events might have on the dynamics of the turbulence and the turbulence spectrum. So there are kind of a number of different ways that the presence of reconnection events may impact your magnetic spectrum. So there's been this kind of recent set of work looking at how, assuming that your onset of reconnection is associated with the tearing instability, you can end up coming up with an estimate for what happens if kind of the time scale for reconnection to onset and disrupt your current sheets is faster than the other nonlinear time scales in the problem. What would you expect if that's kind of mediating your nonlinear dynamics? Then what would you expect for the spectral slopes? And you can come up with different estimates for the spectral slope associated with this kind of reconnection mediated turbulence and come up with different spectral predictions from what you would get from kind of other mechanisms. You could also have that if reconnection is occurring, it may set like a characteristic length scale for the thickness of the current sheets. And that may have an imprint on what the magnetic spectrum looks like. And you could also have kind of reversing that logic that if, electron scale type dynamics and dissipation occurs at some length scale comparable to the electron scales, then that may also in turn have an impact on both the spectrum as well as the kind of scale that you would see reconnecting current sheets at. And so we can take a look at if we see kind of any kind of change in the spectral slope that may be associated with the kind of length scale, the characteristic length scales of our reconnecting current sheets. So what's the kind of thickness of the reconnecting current sheets? And at least for some of the intervals, there seems to be kind of a spectral break that occurs in between the ion and electron scales within the turbulence. Here's an example for the magnetic field spectrum where you have kind of, you have this MHD scale power law. It transitions to this kinetic range power law, which is kind of k to the minus 2.7, which is quite typical. And then right around kind of 4 times the electron inertial length, you get this additional steepening in the spectrum. And it turns out that that length scale for this interval is roughly consistent with the thickness of the reconnecting current sheets that we see. So there may be some evidence that the reconnection has some imprint on the turbulent spectrum, and it could be for kind of any one of these reasons, and it's not entirely clear. We also see changes in various other quantities, spectral quantities, so the spectrum of the current or the electron velocity, et cetera. And so there's an interesting question about how kind of typical this sort of sub-ion scale spectral break is within the magnetosheath, and does it have a clear relationship with the reconnection that we see? So that's some ongoing work that we're trying to look at in the data. But there is this paper from 2019 that I did that at least has one example for an interval where we see turbulence driven reconnection in the magnetosheath. And then another kind of broad open question is understanding what happens as the correlation lengths go to much more extreme values. So we have relatively moderate size correlation lengths in the Earth's magnetosheath. So it goes from kind of tens of ion inertial lengths up to a few hundred, right? But in other plasmas, such as the solar wind, you can get much more extreme values of the correlation length up to kind of tens of thousands of ion inertial lengths. And if you think of this in terms of kind of the scale separation that you have in the system, that would correspond to kind of larger Reynolds number systems in a way, in analogy with kind of hydrodynamics. And so you can ask the question, as we go to these much larger correlation lengths and effectively much larger Reynolds numbers, how does the reconnection change in the system? So naively, based on what we're seeing in the magnetosheath, you might expect that you're going to go towards a system that favors more ion-coupled reconnection. However, it's also possible that maybe as you go to more extreme values, reconnection becomes less prevalent, or perhaps because you're going to much larger Reynolds numbers, you can potentially get additional kind of fluid scale secondary instabilities that then generate much more complex current sheets within the domain, right? We know that in MHD, for example, as you go to much higher Reynolds numbers, you start to kind of curl up the current sheets that you're forming, and you can also get things like plasmoid instabilities that fragment your current sheets. And so does that then lead to kind of a more complex magnetic topology at these current sheets that then would favor something analogous to electron-only reconnection as you go to very extreme correlation lengths? And that's very much an open question. It's something that in principle we could try to look at with solar wind observations, but we would need to have really good electron scale solar wind measurements to look at the kind of turbulent current sheets that are generated in the solar wind at very high resolution. And so with that, I'll leave it with kind of a summary. So MMS is allowing us to look in greater detail than ever before at this kind of turbulence-driven reconnection in the Earth's magnetosheath. This is applications of both understanding the magnetosheath dynamics as well as to understanding more generally how reconnection and turbulence interact within collisionless plasmas in general that may be applicable to other plasma environments. The observations suggest that this kind of novel electron-only reconnection is going on in the Earth's magnetosheath, and this occurs at thinner subproton scale current sheets. It doesn't accelerate ion jets, it has fast superalfanic electron jets, and tends to have higher reconnection rates than you would expect from kind of ion-coupled reconnection. And it appears that the prevalence of this electron-only reconnection seems to depend upon the kind of properties of the turbulent fluctuations, in particular the correlation length of the turbulence. And I think we are at a very exciting opportunity at the moment in space physics for studying the dynamics of turbulence, right? We have these great missions like MMS that's going on, giving us kind of really unique observations of plasma turbulence in the Earth's magnetosphere. As well as missions like Parker Solar Probe and Solar Orbiter going on that are giving us new observations of turbulence in the solar wind. And exciting upcoming missions like Helioswarm, which was recently selected by NASA, that'll be giving us kind of truly multi-scale measurements of the turbulence in both the solar wind as well as Earth's magnetosphere. So I think we have a lot of exciting things ahead of us in the study of plasma turbulence and potentially reconnection associated with that turbulence. So with that, I will leave it open for questions.
All right, thank you, Julia, for a wonderful talk. We have a couple questions coming in, and I have a couple. The first one's from Patricia on slide 15. The amount of energy conversion is a factor of 10 less for the ion-coupled reconnection. Is that typical, or is it because it has a huge guided field?
Sorry, hold on. Said slide 15. Right. So maybe something related to the guide field, although I guess for these two particular events, the guide field is somewhat comparable for the two events. This is a guide field kind of 1 for both of these. So yeah, so it could be, I mean, I guess in principle, this is giving you like a energy conversion rate. J dot E prime is related to a rate of energy conversion, I guess, right? And if you do have a faster kind of reconnection rate within electron-only reconnection, then I wouldn't be surprised if you had a kind of higher J dot E just because you're converting the available energy faster than you would otherwise be doing in ion-coupled reconnection. It's also possible that in reconnection events, you have kind of patchy energy conversion. So it may not all be kind of a uniform value throughout. So it may be dependent on where exactly you're cutting through the event as to what values you see.
Okay. So I have a question regarding slide 10 and the systematic difference you were seeing in scale lengths. Could part of that be observing larger scale processes like Kelvin-Helmholtz on the flanks as opposed to around noon?
So let's see, I guess we're talking about this slide, right? So it could be, but not directly Kelvin-Helmholtz. So we specifically selected the intervals so that you aren't seeing kind of the we aren't getting magnetopause intervals where you have clear Kelvin-Helmholtz vortices going on. So it's definitely not directly those. It is possible that if you have the Kelvin-Helmholtz instability going on the flanks, that may perturb the adjacent magnetosheath in some way, and that may have a signature on the scale of the fluctuations you're seeing. And then that would go into driving kind of the turbulence within the magnetosheath. But it's definitely not directly measuring Kelvin-Helmholtz vortices, but there may be some imprint that could go into that. But there's a variety of different reasons why you might get this systematic variation across the magnetosheath. Either differences in driving, differences in how, like the bow shock geometry that this parcel of plasma went through compared to the parcel of plasma near the subsolar point, could be related to how long it's had to evolve as it went around. So it's definitely an open question.
Perfect, thanks. So Elizaveta has a follow-up question. What do you think about the role of this turbulence in the larger and median scale dynamics of the magnetosheath? Does it play an important role in the overall magnetosheath dynamics?
So I think it likely plays a role in kind of the nonlinear dynamics of the turbulence in a way. Like I said, there's as well as kind of potentially contributing to dissipation, magnetic reconnection also kind of feeds energy back into the through the jets, right? And so it's kind of dictating your nonlinear dynamics. So it's playing some role in kind of how you're exchanging energy nonlinearly in the magnetosheath, right? I would guess that that's more at the kind of smaller scales, so going into the kinetic range of the turbulence. So depending on what you mean by medium and large scale dynamics in the magnetosheath, it's certainly playing a role in, well, it's likely playing a role in dictating the cascade rate within, or dictating the dissipation rate of the turbulence. And I would think that the turbulence itself, beyond just the reconnection events, likely does play a role in kind of doing things like perturbing the magnetopause, for example. So you can imagine that the turbulence in the magnetosheath is going to perturb the magnetic field that's at the magnetopause. And so you might end up with kind of patchy reconnection going on, or potentially initiating reconnection in a patchy way on the magnetopause. So that's how I would guess it would relate to more kind of mesoscale activity, I guess, on the magnetopause and potentially impacting kind of larger scale processes like magnetopause reconnection. Whether the reconnection events embedded directly within this turbulence significantly impact that, I'm not positive, but certainly it plays a role in dictating what the behavior of the turbulence is in the magnetosheath.
And so I have one last question, which comes to, I think, your very last point. The analysis that you've shown is really interesting and quite cool. It seems complex. Will you be able to scale this up in the future for something like Helioswarm, going away from 4 satellites to the, I don't know how many, but larger number with Helioswarm?
Yeah, so some of the things that you might be able to do with Helioswarm would be, so unlike MMS, where kind of you have really good measurements at roughly 1 length scale, with Helioswarm having multiple, more than 4 satellites in kind of a more complex configuration, you have lots of different spatial separations. So in principle, you can kind of directly measure the correlation length a bit better than you can with MMS, or at least in a way where you don't have to appeal as heavily to things like the Taylor hypothesis to get the correlation function. You might be able to do some things with looking at what the reconstructing what the actual magnetic field topology is within the environment in a more detailed way. And that can give you a bit more information about the kind of potential size of these reconnecting current sheets. That could be really interesting. One of the challenges with something like Helioswarm is going to be if you're looking at electron only reconnection, right? Helioswarm is going to be at kind of larger ion and fluid scales, right? So to really get the kind of electron only reconnection, you're going to need a kind of maybe an enhanced Helioswarm that's really targeting electron scale physics as well as those kind of ion and fluid scales.
Okay, excellent, thank you. So thanks again for a really wonderful talk. Next week, we will have a break for the Juneteenth holiday on Monday, June 20th. Following that, though, Dr. Imogen Jinjul will be following up our little series on reconnection, and she'll be talking about magnetic reconnection at collisionless shockwaves. So thank you again, Julia, and I hope everyone has a wonderful week.
Thanks for having me.